So this video for Automata Theory class 5th week homework, and there are two languages, and we need to find if it's regular or not regular. In the class, we learn how to use pumping lemma, and we will try to apply pumping lemma or some different kind of way to understand these languages. Actually, these two languages are really confusing languages because of the pumping lemma actually doesn't work really well in these questions. But I will explain you clearly for both of them. Uh, for example, well, let me firstly explain what is pumping lemma. In pumping lemma, you're trying to apply a rule to divide your word or by the parts of x, y to the power of I and z, and if any value for I bigger than 0 and y value bigger than 0, if all over these word combinations in your language, if it satisfies, your language becomes regular. If there's some problem or some mismatch in your language and your word, it becomes not regular. So you will understand better when we start to solving questions. For example, for question A, it says 0, 1 plus and equalization symbol. If we uh, if we make a word with this uh, with these things, for example, x equals y plus z is a word here. These symbols are inside the word. Don't forget it. And then let me start my sentences like assume. Assume for my language there is a um, there is a uh, finite automata, and this language is regular. Uh, uh, so there is a critical length. Critical length is the length of our finite automata. You can think like that. For your word, it must satisfy this critical length. So there is a critical length m m, and there is a word which is not satisfies this rule word w, where w is bigger than or equal to m. So it's a contradiction. We create a contradiction here. So let's create this kind of word. Could we make it with this pumping lemma way for our word, which is x I to the power of I, y to the power of I, z. If we apply this division to our word, x becomes here, this x becomes this x equal, and y become here y, and what's z? Z becomes x equal here, y here, this is plus z. In this way, for uh, for I to the power of I to the y to the power of I, we will check I equals 0 or 1, etc. We need to check this kind of points, and it becomes like x equals y plus z, x equals y squared plus z, and it continues like that. In a way, as you can see, it satisfies our rule actually. There is no contradiction. Is there? No. But this is, as you can see, binary integer summation. So if you try to make a summation in binary, for example, 1, 0, and 1, 0, if you sum them, there is a carry number which comes here. So as you can see, our um, our carry point makes the x value with the 3 digits, but uh, it doesn't satisfy our root. So there is a contradiction for the length of our word. It's, for example, here the length of our word becomes more than m. So actually, it's not a regular language. In here, you can understand it. It's acceptable. But if there is a care point like that, our language becomes not accepted. Our word becomes not satisfying our rule, so it's non-regular language. Uh, so let's continue with B. This is much harder to understand than question A actually, because W is the binary notation with no leading zeros for a number that is divisible by 3. If you look such a way that and if you write a number like 110, which is divisible by 3, it is 6 in decimal. So as you can see, it's divisible. And if we say 1 is x, 1 is y, and 0 is z, actually if we multiply y um, more, for example this kind of number, it becomes 8 plus 4 plus 2, which is 14, which is not divisible by 3. So our pumping lemma rule is not satisfying the rule, so it becomes non-regular language. B is becoming non-regular language with the basic word 6. But the problem is that there is a finite automata uh, for this rule. So it's regular language, because regularization is that if there is if we can write a finite automata for this language or not. But there is already uh, um, finite automata for that. So for this word, it's not satisfying, but there must be a word that satisfies this 3 rule, this divisibility by 3 rule. So I remember something from my digital classes. There is a method to understand if a binary number divisible by 3 or not, and this is like that. For example, there's a number like that. You are checking digits uh, digit nums, actually digit nums, even or odd. If non-zero elements, so ones, if for one elements, if the in the even digits and odd digits nums are same, it becomes divisible by 3. What I mean, for example, this is position, this is digit num is 1, this is digit num is 2, this is digit num is 3, and this is 4. As you can see, even digit number and odd digit number, there is 2 ones and one of them is in, even one of them is in odd digit number. So this is divisible by 3. Let's check. It's 8 plus 1, 9. Yes, our rule satisfied that. For example, 1100, it's 8 plus 4, which is 12, and this is fourth, this is 30 digits, so it satisfies our rule again. But for 1010, 8 plus 2, which is 10, also this is fourth digit, and this is 2, and there's no more ones in our sentences, so it doesn't satisfy divisibility by 3. It's also uh, not accepted. So here we need to find the correct word for our pumping lemma. For our word, which must be um, written like that, if we write our word like 101101, let's think about that. 1, 2, 3, 4, 5, 6. It satisfies our divisibility rule, so it's most probably divisible by 3. So let's say x is 1, 0, y is 1, 1, z is 0, 1. In such point, for I value 0 to the infinitely many, if we write for I is equal to 0 or 1 or more, firstly it becomes 1, 0, 0, 1, and this is, as we already check, 9, and 1, 0, 1, 1, 0, 1. This is, how much is it? 32, 40, 44, 45, which is divisible by 3, and for 2 it becomes 1, 2, 3, 4, 0, 1. Yeah, this is also most probably divisible by 3. You don't need to check because it satisfies our rule, so it's also correct. It also satisfies, it also returns 1. So uh, in such a way that our pumping lemma works here. So is this language is regular. So these tricky questions are solved in such a way that like that. Thanks for watching my video.